All right, so you're gearing up for your electrician exam? Awesome. You've come to the right place. We're going to sharpen your skills with a little workout session, tackling some real questions you're likely to see. Okay, here's our game plan for today. We're going to kick things off with the fundamentals, physics and heat. Then we'll build on that with some magnetism. And after that, we'll put it all to work on electric circuits. To wrap it all up, we'll do a super quick formula review to make sure it all sticks. You ready? Let's dive in. All right, first up, physics and heat. I'm telling you, getting these concepts right is the absolute foundation for everything else. Here we go, our first challenge. This is a classic heat transfer problem, a real bread and butter question. The key here is just remembering that core relationship between heat energy, mass, and the change in temperature. And look at this. Here's the only tool we need to solve it, the heat energy formula. Heat equals specific heat times mass times the change in temperature. It's a really simple but incredibly powerful little equation. Now, the process itself is pretty straightforward, but Step 1 is absolutely critical. You have to convert your units. We've got to change those kilocalories to calories and the liters of water to grams. Only then can we plug everything into our formula and solve for that final temp. And after running the numbers, we get our answer, 30 degrees Celsius. See? Applying that 300 kilocalories of heat bumped the water's temperature up by 15 degrees. Simple enough, right? Let's keep this momentum going. Okay, next up, we've got a question on dielectrics. This one's really going to test your understanding of permittivity and how different materials can affect an electric field. The solution is unlocked with this really fundamental formula. A material's total permittivity, it's just the vacuum permittivity, which is always a constant, multiplied by the material's relative permittivity. That's it. So all we do is keep that vacuum constant, which is about 8.85 times 10 to the negative 12, and we multiply it by the relative permittivity they gave us, which was 9. And boom, that gives us our answer, roughly 80 times 10 to the negative 12 farads per meter. Okay, time for a change of pace. No calculator needed for this one. This is a pure knowledge check. Out of these common materials, which one do you think has the smallest impact on an electric field? Well, looking at the numbers side by side here makes it pretty obvious, doesn't it? Air, with a relative permittivity of almost exactly 1, is basically the same as a vacuum. It is the clear winner here. All right, section 2. Let's shift gears from static fields to the more dynamic forces of magnetism and induction. Here's another one of those foundational questions, but this time it's all about units. And listen, knowing your units it's non-negotiable. So, what do we use to measure the strength of a magnetic pole? The correct answer is the Weber, or WB. But hey, this table is perfect for a quick review, right? AT is for magnomotive force, AT per meter is for field strength, and AT per Weber gets you magnetic reluctance. Good stuff to keep straight. All right, time to crunch some more numbers. We've got a coil with 100 turns, a certain magnetic flux, and a current. The question is, what's the self-inductance? And here's the formula that ties all of those variables together. Self-inductance, L, is just the number of turns, N, times the magnetic flux, phi, all of that divided by the current, I. So let's just plug in the values right from the problem. We've got 100 turns, multiply that by the magnetic flux they gave us, and divide the whole thing by 2 amps of current. The math gives us our final answer, 2.5 henries. Okay, now for the main event. Let's take all these physical concepts we've been working on and apply them to solve some real, practical electric circuit problems. First up, a conceptual question about capacitors. How does the way you connect them, in series versus in parallel, affect the total capacitance of the whole circuit? So here's how it works, and it might be the exact opposite of what you'd expect if you're thinking about resistors. When you connect capacitors in parallel, the total capacitance goes up. You just add them. But put them in series and the total capacitance actually decreases. Kind of weird, right? Okay, this is a classic AC power problem. We've got resistance and inductive reactance, and our job is to find the true power being consumed by the circuit. We're going to tackle this in 3 clean steps. First, we find the total impedance, which lets us figure out the current. Second, we determine the power factor using our resistance and impedance. And finally, we just multiply the voltage, the current, and that power factor all together to get the true power. And the final answer works out to be 600 watts. Now, it's really important to remember this is the true power. We're talking about the actual energy that's being used to do real work in the circuit, not just the apparent power. All right, our last question for this section is about a very special kind of component. Which one of these materials actually has its resistance go down as the temperature goes up?
The answer is the thermistor. Specifically, what's called an NTC, or a negative temperature coefficient thermistor. So unlike most regular conductors that get more resistive with heat, these little guys are designed to do the exact opposite.
Whew, we have covered a lot of ground. So before we wrap this up, let's do a super quick, rapid-fire review of the key formulas we use today.
Okay, I want you to think of this as your personal cheat sheet for this whole workout. From heat energy and permittivity all the way to AC power and capacitance, these are the core equations that cracked every single problem we tackled.
And that's our workout for today. But I want to leave you with a final thought to take with you out into the field. Of all these concepts we just practiced, which one do you think is going to solve your most common problems on the job? Give it some thought, keep practicing, stay sharp, and thanks so much for joining this explainer.